Hello, I'm Sara Luder from the University of Southampton, and I'd like to talk to you about my work on the conjugacy problem in Wreath products. So starting with some terminology, A and B are both groups, with B acting on a set S, and we call A the bottom group and B the top group. AS consists of all of the possible functions from the set S to A. So in effect, the elements of AS are just a sequence of elements of the group A of length the size of S, which may be infinite. And B acts on AS by permuting the elements of F such that B acts on the element at place S with SB minus 1. That's because you're looking at the element that is brought to position S by the element B. The Wreath product W is a semi-direct product of AS and B. And if S equals the group B, then W, in my terminology, is a wiggle B with no subscript, and that's called the standard Wreath product. So the standard Wreath product, B acts on itself. The permutational Wreath product, B is acting on any set S. So each element of the Wreath product is an ordered pair with one element of B and one element of AS or F. And for our purposes, we always assume that the support of F, which is the elements of F that are not equal to the identity, is finite. So we've only got a finite number of non-identity elements in F, even if S is infinite. And the product law, or the combination of two elements of W, is as set out there. So BF combined with CG gives us the element of B, BC, and the element of F, FCG, where FC for any element of S is FSC inverse. And X and Y are conjugate in the Wreath product if there exists a Z equal DH, such that ZX equals YZ. And if we then work that through the formula for the product rule, we can see that that tells us that B and C must be conjugate in B, and that G D must equal HBFH inverse. Going back to the work of Matthews from 1965, she proved that if A and B are recursively presented groups and the conjugacy problem is solvable in A and B, and the power problem is solvable in B, so you can identify whether any element of B is a power of another element, then the Wreath product is recursively presented, and the conjugacy problem is solvable in the Wreath product. My work is looking at extending the Matthews work from the standard Wreath product to the broader category of permutational Wreath products. For that purposes, I made the following assumptions. So I assume the action of B on S is transitive. That's just for simplicity purposes. I can set S to be B quotiented by H, where H is the stabilizer of some arbitrary point S0. And crucially, I need to be able to determine for any element of B which H coset it belongs to, and also, and I have two elements of S, I can determine whether or not they are in the same orbit for any element in B. From our assumptions, we can see relatively easily that you can partition the set S into the B orbits for any element B, and for each of those orbits you can take a representative element Ti, which means that any element of S can be expressed as S0 Ti B to the J, where J is some integer. If we think of the B orbit order as being the order of B on its orbit, on that orbit, then we can show that if S is in a B orbit OI, then S D inverse must be in a C orbit which has the same C orbit order as the B orbit order on OI. At the heart of Matthews's proof are these maps which take each orbit, each B orbit, to a single element of A being the product of all the elements in that orbit. This map is well defined because we only have a finite number of non-identity elements, and therefore only a finite number of non-identity elements in any orbit, and in fact only a finite number of non-identity orbits. The result of the map is not unique, but it will always be a cyclic permutation of other results. We can extend the Matthews map to the permutational Wreath product, and then we can show that if X and Y are conjugate in the Wreath product, then the pi if for each orbit must equal the pi I dg, which is the orbit of the C orbit to which the orbit is taken under the map. If the orbit orders are infinite, if the orbit orders are finite, then the two elements must be conjugate. And actually, that result also gives us a way of defining a conjugator for X and Y. For the standard Wreath product, Matthews shows that basically gets you pretty much all the way there just by relying on the fact that the support of F and G is finite. But for the permutational Wreath product, we need a different strategy. The first thing I did was to simplify the problem by noting that if B and C are conjugate, then I can actually test whether BF is conjugate to BDG. So I can just set B equals C. So then I'm just looking at B orbits being permuted to other B orbits. And I also can limit my consideration to the finite number of B orbits that contain non-identity elements because the support is finite. So I just divide the support of F and G into its non-identity B orbits. Having identified the orbits, we can take a representative alpha I for each OI and a gamma k for each omega k, and we can calculate this single element of A, pi I f or pi kg, for each of those orbits. We can then list out all the orbits OI, where pi if doesn't equal the identity, and all the orbits omega k, where pi kg doesn't equal the identity, and then we can reorder that list by orbit order. What we're looking for is a permutation that takes OI to omega I, where OI and omega I have the same orbit order, and pi if either equals or is conjugate to, as appropriate, pi ig. That is equivalent of saying that H alpha I d equals H gamma I b to the j for some integer j. Remembering also that the element D has to be in the centralizer of B because it has to permute the B orbits, we end up concluding that if there is a conjugator, then that requires there to be an element D in B, which is in the centralizer of B and is also in the intersection of alpha I inverse H gamma I cyclic B, which is a double coset, and there we're assuming that we've got a finite number of orbits, so we've got n orbits, so it has to satisfy that for each orbit. I'm now working through this solution set to see if there are particular examples of groups where this gives us a solution to the conjugacy problem. Clearly, when you work through it, the first thing to do is to check the size and shapes of the two lists of B orbits. Is there a compliant permutation? If there is, then what you need to do is to check whether there is an element of B that affects that compliant permutation. If B is finite, then that's easy to check because you can just check every element of B. Also, if the centralizer of B is small, and then as that we're looking that the intersection includes that any element that's any compliant B must be in the centralizer, we could possibly just test all the elements in the centralizer. And of course, if B and S are both finite, then there's probably a much more efficient algorithm to doing it. So this is really only of interest when B and S are infinite. So that was a very rapid run through of my results so far. If anyone would like to discuss them, please do contact me.